Morning, everyone. So, we're just going to recap a little bit of the electrical configuration stuff we've been dealing with over the last two lessons. So far, we've done two different types of electrical configuration. One is what's called a full electron configuration. Because it is a full configuration, this is a roster of every single electron that you have. We saw that especially as we started looking at examples like hafnium, like uranium down here. If I'm having to track the electron placement of all 92 or all 72 electrons, the list gets to be fairly long. So typically for full electron configuration questions, they're only going to ask you up to about krypton or so. That full configuration will go something like 1s2, 2s2, and going on from there. Remember, the placement on the periodic table will tell you what the ending one should be. So for example, if I were doing silicon I notice is in row number 3, period 3, so n equals 3. It's in P block. Remember, these 6 columns over here are P block. It is the second element in, so I would predict silicon's very last electron, as you fill up the roster here, should end in 3p2. But for a full configuration, you don't just want to just say 3p2. I know that's my very last electron. Silicon still has 14. I would expect to see all the inner shells up until 14. The other way they can ask you a question is using core notation. Core notation is that simple electron configuration. Core notation uses the noble gas to hide the inner shell. So we're going to hide closed shells, the inside shells here with the noble gas, with the exception of helium. Remember, for this memory aid here, helium is typically sitting over here. So that's going to be 1s2. 2 electrons closes your first shell. The other noble gases, we're going to have row 2, 2p6, or 3p6, or 4p6. We're going to look for a very last p6. That's going to close any innermost shells, and then they can ask you core notation. Typically, they'll ask you some of these bigger ones because it's going to be a lot easier. We would just use the noble gas to hide any inside shells, and we just tack on any leftover. So just recap again. For core notation, we use the noble gas. It hides any inner shells. And those inside shells are bound to be full because we're off-ballowing, we're pretending things are in the ground state. So those are all hidden away. It got a little bit scary towards the bottom here. I did the 6s row with you. Let me do an example. Let's say with this francium row. Francium and radium are in S block. Francium would have been 7s1, radium would have 7s2. All these elements over here will at least have radium 7s2. Just like in the earlier row, actinium is in D block. The D blocks here, remember, are one row shorter. So because this is 3D, if you count your way down, 4D, 5D, actinium would actually have the 6D1, so that's electron number 89. But electron number 90 is not Rutherfordium's. Element number 90 is actually down here. As you skip over down here, remember this is into F block. And F block, these were 4Fs, these are now 5Fs. For the 6Ds, we still do have the 5 rooms of 6D, but by the time you get really to the top of that hotel diagram, we're getting these orbitals being so close in energy that, sure, actinium has picked up 1 electron, but then we start going thorium, oh, now it's 5F, and it's the first element in, 5F1, this PA here, 5F2, all the way through. Unless we fill up all 14 of these extra electrons, we don't come back for 62 later. So in an example like uranium, uranium would be 5F1, 2, 3, that would be it. We would still have the 61 that actinium had, that's this one here. And because we didn't quite make it through F block, we're going to end it off there with just 5F3. So if I don't make it back, right, then I don't pick up any more D electrons. If I do make it back, again, we don't want to do something like blah blah 61 for 5F. I don't want it to look like 5F, oh, I made it through the S and then now I'm coming back for the D's. I don't want to write it separately because then that gets a little hard to see. The left-right order doesn't matter. If you notice, oh, we are coming back and we are starting to pick up the extra D electrons, either drop it from the beginning and start going 62, 63, 4, 5 like that, or you can just, since we already had a 61 here, we can still go 61, 62, 63, so on and so forth. So I hope that flushes out a few things. We did talk about doing ions as well. For ions, basically we take the element as they sit on the periodic table. There were 2 rules. If I were forming anions, the rule was add to the next lowest energy as well. Right. So let's do another quick example here. Say we did fluorine. Fluorine has electron configuration 1s2, 2s2, 2p5. That's unstable. Fluorine is going to gain 1 electron. It's going to be plus 1 electron. When it gains an electron, it becomes F minus. Oh, sorry, here. Skipping ahead of me here. So fluorine should have been 2p5. And only after you gain 1 extra electron, for my 2p rooms, so far I had 5 people inside. When another electron arrives at the hotel, we would then put him on this last shell here. So this one now would be 1s2, 2s2, and then 2p6. Okay. That one there is isoelectronic with neon, which has a noble gas of it, so 2p6 as we expected. So anions are fairly easy. Cations have that strange order. We're going to see a little bit of a reason for that in this lesson here. So cations, we are going to remove electrons. So the guests were already inside the different rooms, inside the different orbitals, but what we're doing here is we're trying to pull away electrons. To remove electrons, there's a special order, in order P first, then S. These two are referred to as your valence electrons. These two are the outermost shell. Once those are gone, then like layers of an onion, then you can tackle any inside shells D and F. But be careful when you use this rule. This one here has to be on the outer shell. So I might have, let's say, 2p6, but if I have energy level 3s coming off first, 3, doesn't matter what it is, 3d or 3s, whatever, those will come off before 2p because 2p is a part of energy level 2. So let me just do as another example for you here. Say we did the full notation. Let's do another BM, NB. Yeah. So NB is element 41, which means it has 41 electrons. Let's predict where the very last electron would end up. So we are on row number 5. We would definitely have 5s1, 5s2. I'm just going to write that as 5s2. Entering into the D blocks, the D's are 1 smaller, so this is 4D. And we're the third element in, so now it would be 4D. So let's start from hydrogen and helium. We're trying to do niobium here. We're going to go 1s2, 2s2. You can check your work here. As you get more familiar with this, the ordering should come very naturally to you. We just talked about here, it should be 5s2, and then you're up with a 4d. If I add up all these superscripts here, it should give you the total number of electrons this niobium has, and in this case here, it's 41 electrons. When I start thinking about the different shells, remember our noble gases closes our shell for us. So 1s2 is helium, that closes the first shell. The neon closes the second shell. P6 will mark the close of the shell. So close the third shell, closes fourth shell. We talked about here, consistent with the Bohr model, the Bohr model first shell only holds a max of 2, and second shell holds a max of 8. Depending on how you do shell number 3, we could say 8. That's the way I prefer it, because that's the 8 valence electrons that the Bohr model shows. But technically, because all 3 of these are energy level 3, there are 10 other electrons that actually belong to n equals 3. It was just that energy level 3 when it split, the 3s, the 3p, and the 3d. It's just that the 3d ended up being higher energy than the 4s, which is why we actually started filling the 4s before. So just wondering, we started filling the 4s before we did the 3ds. But still, it is energy level 3. So if I go 8 plus those 10 there, that's where I get my 18. Okay. So there's my niobium here. Just introduce to you a couple other ways this question can be worded. Once you have the full configuration, it started from 1s, it can ask you how many unpaired electrons you have. Now, unpaired electrons is usually going to be, well, the outermost shell. I would imagine I packed all the rooms going in at lower energy, going only to upper floors when I needed to. So when they start asking you the number of unpaired electrons, we are really only interested in this outermost shell. Careful, you can't just look for odd numbers to figure out how many unpaired electrons it has. You do want to draw one of those orbital and box diagrams. So on floor number 5, a 5s kind of room. So far we have a 5s2, definitely no unpairing there. When you have 4ds, remember the d's come as 5 rooms. You can maybe just draw 5 lines or even 5 individual boxes. This is sort of testing your understanding of Hund's rule. Hund's rule says, like on a bus, people go in one by one. We're going to take our own seat unless we really, really have to take another person's seat. So in this case here, we have 4ds. There's 5 individual 4d orbitals. Therefore, each room itself is called an orbital. So that's 5d orbitals. But because of Hund's rule, we only have 3 electrons. There we go. We have 3 unpaired electrons. What if I did another element here, and what if it was a 5s2 and a 4d7? Again, it's not immediately obvious. You can't just say, oh, easy, odd number, 7 unpaired electrons. Again, given the 5d rooms, if I do 7 times rule 5 people in, this would actually, in chapter 3, it's going to make it very paramagnetic because all the spins are parallel and I have 5 unpaired electrons. But now that I'm going to double back on myself, and now that I'm going to force electron 6 and electron 7 in, again, we have an example of 3 unpaired electrons. So be careful when you use Hund's rule when you're counting unpaired electrons. That's what I do from there. Negative anions are not that hard, so if I suddenly made this one here, what would niobium minus 2 look like? This is not going to be niobium's normal charge. This is a metal. It's supposed to be positive charge. But basically what happens here is you're going to see if this is a negative charge, that means I gained 2 electrons. And if I gain 2 electrons, those electrons can't fit in any of these under shells. They're going to have to fit into this really, really top shell. This top shell here so far had 5s and 3d, so 4d. Started off like this. 1, 2, 3. And what if 2 more people arrive at your hotel? They also want to be as close to the core as possible. Unfortunately, all these inner shells are filled up, so they're going to go in 44 and 45. We did see an exception for chromium and copper yesterday when we were something like 5s2 and 44. It was a little bit of an energy input to get the electron going upwards to promote that one, but the amount of stability I get for a perfectly half-filled shell or full shell will pay me back for what I end up putting in. The only exceptions we need to do are the chromium and copper. Let's say in this case here, I was already 5s2 43. I'm not going to promote both electrons up just to get that half-filled shell. So the only time I see the exception are the 2 that we did, copper and chromium, as well as the column diamond. What if instead niobium, being a metal, it typically wants to get, let's say, a positive charge. Let's say niobium plus 5. Now naturally, as we were adding our electron configuration, the last 5 electrons I was doing was the 5s2 4d3. It already was energetically here, so 5s2 4d. I was slowly adding the 43. Again, the guests are already at the hotel. This one here is the highest energy. We would have imagined the 4D, which got filled last. Since I put those ones in last, those are the ones that come off first. But if you do your rules here, again, I can't touch any inside shells. Core notation does a really good job of this. The core notation will hide the inside shells for you. The 4th noble gas here is krypton. Krypton indicates for us all 4 inside shells. So krypton hides the 4 inner layers. The only layer that we're interested in is currently the 5th layer. That's the outermost layer of the onion. And on this outer layer, do I have P's yet? Well, no, I don't have 5P yet. Do I have any S's? Oh, sure, I have S's here. This is actually energy level 5. Even though these electrons were not the ones that I put in last, these are the ones that will come off first. So as niobium loses electrons, I'm going to pull this one out, pull this one out. That's going to be niobium plus 2. Once the 5s2 is gone, there's no point in writing it there. Then we're going to come back and we're going to drop. What if I pull up third guy, 42, 41, and then in the end we're going to cancel out the whole thing. So niobium here will be isoelectronic with just a krypton up there. So we have pulled off the 5s. So remove 5s before 40. Even though the 4D were the very last nickname there. So, hopefully that clarifies a few things from yesterday. Today what I want to do with you is I actually want to introduce to you some of these shapes. So we've been using the placeholders P, S, D, and F to try to figure out what the electrons are actually doing if they're not actually in orbit. We're going to get a sketch of what these orbitals look like and hopefully flesh out a little bit of the understanding. This part here does get a little bit technical, but I thought it's important for you to actually see what we're actually listing when we do electron configuration. So, just for a little bit of theory here, we're going to step into a guy called Heisenberg uncertainty. So Heisenberg uncertainty. There's a lot more detail to this, but I'm just going to hit some of the main points. For Heisenberg, through his experimentation, he came up with the idea position and the momentum. If you're not familiar with physics, that momentum is related to velocity. So I'm just going to throw the word velocity in there. The position and the momentum of electrons cannot be known. So I'm making this thing. The position and the momentum of electrons cannot be known at the same time. You can't know both. Now the question comes to, well, why not? Okay. It's just in our universe, electrons have this funny behavior. So how you can think about this here is, let's imagine I have an atom, you have a nucleus. We know the electrons are somewhere out here. They may be on shell 1, shell 2, I'm not sure. Okay. We know the electrons have to be somewhere out here. But if you do an experiment and you go looking for the electron, what Heisenberg's uncertainty says is, if you're able to actually pinpoint, say I have a super powerful microscope, and you can actually say, aha, that's where my electron is. The electrons have this very funny property. The better I can isolate where the electron is at this point, the less I know what it's doing. If I can sort of put my finger on it, aha, this electron is here, I have no clue. Is this electron zipping off this way, or that way, or this way, or this way? The worse and worse I know where it's going. Or vice versa, if I know the momentum, or if I somehow, let's say out of my periphery, I end up seeing an electron zip off in this direction that quickly. The better that I know which direction it's headed and how fast it's going, there's an inherent uncertainty to our knowledge. There's an inherent uncertainty to, well, where is that electron? I can't really put my finger on where it is. So electrons have this sort of duality. They sort of have this funny principle that I can't know its whereabouts as well as what it's doing, where it's headed, where it came from at the same time. In science, things that behave like this are referred to as having a duality. Just as an example, light also has this dual nature. So similar to, sometimes we call it the duality of light. Light can be understood as a particle. You can think of light as little packets, little photons of energy, or light can be understood as a wave. So waves, they don't just travel in straight lines. When they wrap around single slits, double slits, they actually curve. Okay? They can be a particle, or they can be a wave. So as a wave here, we have our electromagnetic spectrum. Pretty much in science, if it's easier to understand as particles, think of it as little packets. So the Planck's formula that we did so far, as a laser beam here shines light particles, you can imagine that laser beam here is full of little packets of energy that just travel in one direction. Or if we're interested in looking at spectroscopy, looking at how much energy these waves carry, I might want to do something more wavelength. Again, it's not necessarily that the light photon itself is actually zigzagging back and forth. Light just travels in this just straight direction. But what we're actually having is, by showing the wavelength, is I'm actually demonstrating for you the energy that this photon is carrying. So particle nature, wave nature. In this case here with Heisenberg, he says electrons, which we're very comfortable thinking of them as point particles, electrons also have this duality. Electrons can behave as either particles, as little bits, okay, like photons, or they can behave as a wave. It's a little bit weird to think about electrons. What if they don't have mass? And what if they're actually having a more wavy nature? They're not actually solid particles I can put my finger on. So in this case here, the particle nature, this one here, this is like, we have electrons as particles that orbit nucleus. Okay? So that's the particle understanding. To start introducing this wave understanding of this here, the wave, this one here is a mathematical function that basically describes for the electron what it can do, what energy shell it's on. We're going to see this actually relates to the orbital shapes in a second here. This wave function here, we're going to give it a Greek letter psi. So this wave function looks like a pitchfork. Essentially, it's an equation that just describes for the electron when an electron behaves as a wave, when it's not super clear where the electron actually is, and it's just having traveled from one place to the other. This function describes its nature. So just a quick analogy for you here. I'm going to put up a quick clip from Big Bang Theory. You can take a look at this time here. The analogy we're going to use is an analogy called Schrodinger's cat. So Schrodinger's cat. It was said that Schrodinger did have a cat, but he never did this experiment on his cat, fortunately. You can go watch the clip right now. So based on the clip there, we're told we're going to have a cat. So artist cat. here, we're gonna just sort of hypothesize that this cat is put underneath a box. Let's say this box is made out of cardboard. Unlike this picture here, we can't actually see through this box at the moment. But the cat is basically put in this box here with the sealed vial poison. So this poison here is deadly for the cat. I imagine that this top of the poison is made out of maybe like a cork top. You know, it forms a fairly nice seal, but it's not perfect. The question, or this analogy here goes on, again, it's nice that Schrodinger didn't do this to his cat, but the question that he had was, I have my cat, I have my poison here, I want to know, is my cat dead or alive? Is my cat dead or alive? Well, since the box is over top of it, I'm not sure. So let's think about the options. Why would my cat be dead? If the poison has had a chance to seep out, cat breathes poison, oh, there, dead cat. Okay. Why might my cat still be alive? Yes, the poison is deadly for it, but let's say the cork has a really good seal on it, it didn't burst open, it didn't sort of go into the chamber here. My cat is just still happily minding its own business there. Okay? So in some sense, we are saying, I don't know. Right? Because the box is over top of it, it sort of clouds what the cat is doing. I don't know whether dead or alive. Instead of being in a state of just saying, I don't know, the cat can be thought of as being in a state, kind of funny. The cat can be both dead and alive. Now traditionally you'd say, well, how could it be? These two are opposites. You're either dead or you're either alive. But in this case here, in my uncertainty, because the box is over top of it, the cat can be in this funny middle state. It doesn't really need to decide whether it's dead or alive because nobody's looking for it. How would I know for sure? Well, what happened then is because the box was sort of clouding over what the cat was doing, if I take a measurement, if I go and do some research, if I do an experiment and I lift out the box, only then does my cat need to decide, oh shoot, someone's watching me, so then I need to decide, oh, I'm going to either appear dead or I'm going to appear alive. As long as the box is over top of the cat doesn't need to make this decision. So, yes, these two are opposites. Yes, in some sense I'm saying I don't know, but in this case here we're saying because nobody's looking for it, the cat can be in this funny state. This analogy here carries over to electrons then. When we start thinking about electrons, well, are they actually particles or are they actually waves? Electrons, like this cat, don't need to decide where they are or what they're doing unless you go and make a measurement. Unless you actually go and look for it, I don't need to tell you what I am. So in this case here, the conclusion from this analogy, electrons don't need to take any position. They don't have to appear anywhere. Like the cat here doesn't need to decide whether it's dead or alive until a measurement, until you go looking for it. Unless you go searching and wondering what it's doing. So until you actually go and lift out the ball, then the electron has to decide, then the cat has to decide. In some sense, it's a little bit strange because when we go to make a measurement, we're sort of taking the cat away from the analogy that it is right now. The cat was in this funny dead and alive state. It only takes a decision once I go looking for it. So I sort of screw up the system by making a measurement of it. When I go looking for it, I've actually changed what it was doing initially. This is actually what we've been drawing for our orbitals. For our orbitals are actually regions in space. Sometimes it's sort of described in 3D here. It's a region where your electron is likely to be found. Instead of actually deciding for certain, aha, you're right here, aha, you're going this way. What we're doing is we're actually just sort of marking off a space, marking off a place where the electrons might end up appearing. Back with that funny psi symbol that we had earlier, this one here was called your wave function. This one here was a mathematical equation that sort of describes the electron. Just like in math class, functions can be positive or negative, because we live in a space that's positive, like sort of positive distances here. What orbitals are actually going to be is they're actually going to take the wave function and they're going to take the absolute value squared. If you want to get really fancy here, this guy here is typically called a probability distribution. This one here sort of marks off a region in space. These are quite complicated. These are 3D functions, so it's going to be really hard for us to draw. But these are probability distributions. These are places where the electrons might appear. So I'm just going to start sketching for you some of these orbitals here. Let's imagine taking our regular x and y 2D plane, so horizontal and vertical. Imagine this were a piece of paper, and imagine just lying this paper just flat. So So we have our x-axis, our y-axis actually pointing into the plane of the page. This allows me to actually get a z-axis off of it. So this is a right-handed coordinate system. So hopefully you can start seeing that in 3D. Some of these orbitals here will make more sense when I actually draw them out in 3D. So as we start looking at the s orbitals, p's, d's, and as, we're actually going to see where are the regions of space where I might need to find them. So just as an example here, let's do lithium as practice. So lithium has a configuration of 1s2, 2s1. IB wants you to know two types of orbitals. One type of orbital here, s orbitals, are always spherical in nature. So these ones here in some sense are a little bit boring. So let's say I have a 1s orbital. I'm going to have a region of space. Let's imagine this is like a tennis ball or some sort. Okay. There's a region of space. I'm just doing this as dots because it's just a probability. It's not necessarily that the electron is everywhere all at once. But like the cat doesn't need to decide dead or alive, the electron doesn't need to decide where it is just yet. So this one here is my, let's say, my 1s orbital. Because it's s, it's spherical in nature. As long as I don't go looking for it, when I have these two electrons in 1s2, those two electrons can be anywhere inside that red shape there. When you go and metaphorically lift off the box, or when you go make a measurement, you're asking, well, where is the electron? When you go looking for it, the electrons somehow know, and the electrons, instead of being in this funny dead or alive state, the electrons will naturally say, oh, I'm actually over here, and I'm actually over here, I'm spinning this way, spinning this way. The electrons only appear when you lift up the box, when you actually make a decision. When you look away, the electrons can relax again. The electrons don't actually take on any spot. You take another observation and you look at where it's coming from. When you take a look, oh, the electrons somehow realize, and maybe both electrons are appearing on this side. The electrons don't need to take on the spot unless you actually go make an observation, until you actually go looking for it. So that's the funny nature that electrons have. S electrons are spherical in nature. What's the difference between something that's energy shell 1 versus energy shell 2? Just like with the Bohr model, as the energy level, as the number of shells go outwards, shell 2 should actually be a little bit further out. So this one here is actually going to be 2s. In this case here we have a 2s1. So inside this green sort of dotted diagram, it's a probability distribution, it's an orbital, it's a place where I might find my electron. When you go looking for it, the electron in 2s will realize someone's looking for it, and the electron will appear somewhere in that 2s shell. So this whole notion of orbitals here, region where you might find it. Another analogy is, let's say I've just realized I lost my keys. Okay, so what I'm going to do is I'm going to look in places where I've been. I'm going to check my pockets, I'm going to check my bag and whatnot. These are places that I've been. I'm not going to bother flying to Toronto. I haven't been to Toronto today. So there are places where I want to go look first. So these orbitals here are actually marking off those places. So just to finish off here, our p orbitals are a little more interesting. What if we have, you know how p rooms always show up in sets of 3? We could actually call them px, py, and pz. P orbitals are typically in the shape of dumbbells. So they're like weights that we lift in gym class. So for a dumbbell, what's going to happen, let's say I have a 2p. Sometimes we have a px. It's called px because along the x-axis, it's like a dumbbell shape. It's large on either side, and there's not a lot of chance that it can be in this middle section here. But that's on the x-axis. On the y-axis, that's going to be the sort of in and out axis for my diagram here. I'm going to color code it for you. So py marks off a region of space. This is sort of like a probability distribution. The electron could appear anywhere within that shape. Doesn't really need to take on a spot until you're looking for it. And finally, we have pz. Again, color coding it. The z refers to that third axis. So we call it the azimuthal angle. So we have the pz, also dumbbell shape, but that sort of marks off a dumbbell shaped region where the electron might end up appearing. So in that case there we have 3 p orbitals. They are all 90 degrees from each other. Let's say I have something like oxygen, which has this configuration 2p4. When the box is over top of it, the electrons don't need to decide. When you go looking for it, however, when I decide, these orbitals suddenly vanish, and basically in the px, I would expect 2 electrons to show up. They could both be on the one side or the other side. We call these orbitals here lobes, but these are just places that the electron might appear. In the py in the green, when the box is off, the electron might appear somewhere there. In the pz, one electron shows somewhere. So electrons have this really, really funny property where they don't really need to take on any spot or any location unless you actually go looking for it. I'm going to attach a nice link here to nice pictorial diagrams for these orbitals. You can play around with it. Just going to pull it up really quickly for you here. You'll notice on this link here we have our different orbitals. Our 1s is showing you as a spherical diagram. You have the configuration on this corner here. 1s1 and helium 1s2, they're both in the 1s orbital, a spherical shape. The electron doesn't need to take on any spot unless you go looking for it. We just did lithium. They are sort of limited in size here. If you imagine the orange was this big, the blue would actually have been a little bit larger. In this case here, the orange is sort of superseded by that blue there. 2 electrons should appear in the orange, 1 should appear in the blue. 2s2 similarly. Here's those dumbbell shapes. Don't worry about the blue and the orange. This is actually indicating for the wave function when it's positive or negative, but by the time you square it, it's just giving us orbital. So looking at 2p, maybe this one here is 2px. Because they're 90 degrees, you should be able to see that these dumbbells flip back and forth. We do our Hund's rule, so I go single, single, single. So px, py, pz, and then I double back to myself, px, py, pz, py, pz. And then going on from there, as I go to shell number 3, 3 circles inside each other. We have a dumbbell and a dumbbell, px, py, pz, px, py, pz. You can definitely play around with this a little bit more. In chapter 3, we're going to come back and we're going to look at the d orbital shapes. The d orbitals are even more fancy. Again, don't even worry about the orange and the blue. D orbitals are typically like a butterfly shape. They're also switching 90 degrees. One of them is really weird. It sort of looks like one of those baby pacifiers. So we have d orbitals. They all look like butterflies. This orbital may actually have 4 lobes, but that is just one d orbital. Being one d orbital, the Pauli exclusion principle said you can only have 2 people in in some of those lobes. So both of them could be in the orange, one can be in this orange, one can be in this blue. They only need to show up when you go looking for it. Again, we've screwed up the system. By looking at it, the cat has to decide whether they're alive, the electron has to decide where it is. You see chromium actually has an exception. This is already promoted its 4s1 into the 3d5. And as you go to manganese, again 2d5. We double back on ourselves. I'm not even going to worry about the f's, you can play around with them. Okay. Really, really complicated shapes, lanthanum. Just have a look at some of these diagrams. Although the shape is different, the understanding is the same. The electron should show up somewhere in that shape. So that's where we'll end off our lesson for today. We're going to finish off with ionization energy in the next lesson, and that'll be it for chapter 2. Thanks guys, take care.